So this is part 2 of Cadence tutorials. I will cover how to make schematics. We'll run a small simulation just for the sake of covering that part, but then go into a lot of detail about schematics, how to use, how to even generate and save system Verilog designs, which you can use in your simulations, and hierarchies, shortcuts for making schematics, symbols, and all this linking, etc. Believe it may have been covered in the previous lecture, but I'll still just make a new library just to show that part again. So this again I would recommend not to make your libraries in the same folder where you have your cadence, in terms of like just uh, backup and all this. Among other things, it will make things easier if you keep all of your libraries in a separate folder, like here for in libraries slash tutorials. I've done this, and you attach it to your PDK and you're done. This is your library now. In case you don't attach it, if you already made it, you can go to technology file manager and attach from here. So yeah, attach this way, apply. So we have this, we want to make a schematic in this. Let's start with the inverter and try to just simulate it. So what this means is you can have some name for the view and there's a type for the view. So this written thing here, schematic, doesn't really mean much. Mostly no one changes it, everyone like keeps it to be schematic for layout, everyone leaves it to be layout. But this is what really matters, whether it's this is schematic or this is system Verilog or this is layout. So that is what really matters. So it's like you have a file, the file will have some extension like JPG, PNG, like a image format or a video format or a executable format. So this type is like that, and the view is just the name of that file in a way. And your cell name is a container rather than a single design. So because you can have multiple schematics for a single cell, you can have schematic, you can have schematic v2, you can have schematic backup. So all of them being independent. They won't be completely independent because of things like symbol, but uh, as far as simulations are concerned, they are pretty independent. So now we'll just make a schematic here, and let's just add a nmos pmos from gpdk nmos, and we just want it to be some minimum sized. So I'll just write 10 nano and it should give me the lowest width. Yeah, then it sets it to 400 nano. Fine. Once this set, you can hide it, or even now it's like just put it here. Similarly, and the shortcut I'm using, either you can click on this add instance, this create instance, or press I. Important thing to note here is Cadence is very particular about its shortcuts. Capital I and small I lead to different shortcuts. This will be helpful later as well. So please keep in mind whether your caps lock is on or off, because these shortcuts may not work in when caps lock is on. So again, another PMOS 400. Let's see. Yeah, 400. Again, you can do wire by clicking on this create narrow wire, or by pressing W. This is again small w, and what you can do is click on this, it will make the wire. For undo, it's U, small u. What another thing you can do is, when you're in this mode to make wire, as you can see on the cursor, you can press S and it will select wherever this diamond is there. It will start from there. So press S and now you have a wire from there. And now here again the diamond is here. So even though my mouse is here, a bit away from it, it will still snap to it. So you can use this to really quickly make wires. Uh, so wherever there's already a node connected, it won't latch to that. So it's just something to keep in mind. Now I will demonstrate a very basic method of setting up a test bench. You can do it if you are doing things for your assignment. It is really not recommended if you are making any project, if you're working on some project, working on some tape out. Just to show things, I'll make that, then we'll move to the better practices. So net name, v in, v out, vdd, and then ground. So this dialog box appeared because I pressed L, and you can remove it by pressing escape. You can just write v in, escape, and then just keep it there. Otherwise what you can do is keep multiple net names. So v out space vdd space ground, this way, and you can put all of them separately. And when you have something like this, you need your sources, like your input. So that input will come from analog label. There's your vdc. You give an input of v in, voltage. You can just copy paste things. For copy, you press C. So when it's selected, C, click somewhere and then it will copy it over. Yeah. Yeah, and you can edit the names just by double clicking all this. So now you have this. You can write numbers here as well, or you can write some variable here, and just AD Explorer, create new view. It will be called Maestro. This also you can have multiple Maestros with some different name, Maestro backup, Maestro with some date, all this. Spectre simulator, we want to do a DC analysis, save the operating points and sweep a design variable, which is your input voltage we want to sweep. But here you can't really do that because it says no design variables found. So I'll just show how to solve this. Design variables, as of now there's no design variables. Copy from cell view. So now they are available here. Now you can just write here 1.8 This is okay, 0.9. And now if you ask it to select some design variable, these are visible. Start from 0, go up to 1.8. If you check in the help and all this, you'll see that it creates like 50 different points and goes through them. And the sweep you can specify to be linear with some step size, number of steps, etc., or log. If it's frequency, you may want a log. Yeah, so it's just this, nothing too complicated right now. And just this is not enough. You should save the outputs. How do you do that? Outputs, add, sorry, outputs to be plotted, select on design. You select your input as well, output as well. So you want to see VDD also, I'll save here. And even though you add this, I would recommend check the save option here. I'll go into the save and like what does this mean, save, but for now I'm just keeping all of this on. And just run this. In case you feel like the simulation you like tried to start it but is anything happening, you can look into the CIW window, the cadence terminal. It will contain all of this information. So where it's trying to run the simulation and like whether it got some error, etc., you'll see that here. What's where the results are being stored, etc., all will be present here. So yeah, and you get this one more window, which is your Spectre output. Spectre is your simulator. When the simulator is running, it will say what's the all the settings, what's temperature it's running at, and the tolerance levels for the current, voltage, all this, and what type of convergence method it's using. It's if it's not converging, all of this. We'll go into this part as well in more detail in the later parts about the simulation, just covering the very basics here. And you can just see the thing here. You can hide them, separate them out, all this, change the type, etc., style, color, width, all this. Pretty basic stuff. Now that these basics are covered, go into how to make a schematic. We have the schematic. This is a really bad way of making schematics, because whenever you have something, and also this ground thing I'll explain, whenever you have a design which you want to put on a chip, all the schematics that you're making, if they're not a test bench, if they're the design, they should not contain anything, absolutely anything, which you can't put on the silicon, which you can't uh, realize in actuality. So you can't have things like that VDC. You can't have things like IDC, your ideal current sources, ideal voltage sources. They don't exist in reality. They're just simulation tools, simulation uh, ways to simplify your simulations or make them work. So never ever include them in your schematics. In test benches you can include them, but only in test benches you can include them. I've seen this happen a lot of times where people include these things in their designs and then shift delete them. Shift delete as in ignore. You select any device and press shift delete, it just ignores it. So in your simulation this won't appear, it will be ignored. Never do this. If you have a design, just keep it a simple design which you can realize on silicon. Second thing, once you have something like this, never include things like ground this way. So this ground and then your exclamation mark. This means this is the absolute ground of your simulator. uh, because if you just write ground or something, then it's a different kind of node. It's some node. If you just write gnd, it's a node. V in, V out, VDD, all of these are nodes. If you write gnd and then exclamation mark, then you can see here it's written 0 here. So this is defined to be 0 volts. It's just a simulator uh, way to tell the simulator that this is absolute 0 volts, right? Because you need some reference for all of your voltages. So never ever include GND and the exclamation mark in your designs. That will also cause issues because you that doesn't exist in reality. You will have some node as your ground, not some value which is some absolute 0, right? You have some GND, you have some V out, V in, VDD. You want to use this and integrate it with some other things. Maybe you want to make an inverter chain. How do you do that? You need to make a symbol for it or something. Even like op amps and all this, they have all these symbols so that you can integrate them on a bigger level, right? For that to happen, you need to have ports. So like an op amp internally may have a lot of nodes, a lot of devices, but what you really care about is just your input, maybe your differential input, maybe your differential output, the supply ground, maybe some bias current. That is all that you care about. Internally, there may be 100 nodes present inside. You don't care about them. You just care about these input output nodes, the power nodes. How do you define that you just care about those nodes and those nodes you want to use in the upper hierarchy and you want to use them in a symbol or something? So you add pins for them. So small p, you can open this dialog box or even like this thing, create pin. So small p gives you this create pin. Now there's V in, there's V out, VDD and ground. Now the reason I've put all of these in capital has something to do with how Caliber handles net names. It's too complex to get into right now. In the layout part, I'll get into it. But I would recommend if you're going for a tape out, and for the sake of uh, keeping things consistent, try to keep everything in the same format. The format we usually use is just keep all of them in capital and all the ports as input output. Although some higher amount of value can be achieved by defining the direction and the signal type specifically for each port. So it can help you debug things a bit easier. It can make things a bit easier. And then and you can delete the names, the previous names that you've given. You can delete them because these will get the name which the port is associated with. Now, even this is not really recommended because your VDD, if someone is looking at this name, it doesn't represent much. It doesn't say the VDD is 1.8 volts or 5 volts or what. So better to keep something like this. And if you put dot or something in your net name, that may also cause issues. Hence, try to use like underscore or something. Sorry, try to use like p or something instead of a dot, a point. And to be even more verbose, you can write things like dvdd, and this is your d ground. Because this is an inverter, it will be used in digital circuits that way. So this is like when you have a larger circuit or something, then it makes sense to be more verbose like this, so that you don't need to go inside and check whether this inverter should run at 1.8 volts or 5 volts or what. uh, so that's some of the like best practices for making a schematic. Another thing is the a few shortcuts associated with it. Let's say you have this, you want to move this, press M and can move it. I'll move this as well. Otherwise, I'll show one more thing here, which is the advanced options. As in, you have this thing, the design. How I'm selecting this is you select one thing, press shift, and then select the other things. If you press control, then you can remove things from your selection. Select all of this, then copy C, and then you can just copy it anywhere. Now this copying is fine, but while you're in the process of copying in this zone, you can press F3 and it will give you these advanced options for copying. So you can do copy at any angle, or diagonal, or orthogonal. Orthogonal is what you'll most probably see. And even like leaving that aside, you can do things like rotate. So yeah, I think it's pretty like self-evident what these things will do, upside down and sideways, etc. You can paste things multiple times. So this way, you just click it once and then click it once again. So here you have 4 more copies of it. What one more thing you can do is that angle I said. So copy, it's trying to copy F3, and now you can say orthogonal. What orthogonal is, look at my mouse. It is not at the same angle, and I'm trying to move it, but it will still stay at the same x of this. Sorry, at the same y of this x we can vary. So it can, if you have like uh, you want to keep things all of them in line, so this can be helpful. And again, copy, you can put like multiple copies of it. This, yeah. So you can very easily just do this. You can just copy individual nets as well similarly, and in order to change it, press C and F3, you can change it back. Same things apply for moving as well. Let's say you want to move this, move, and here you can say at what angle you want, uh, how you want it to direct the wires. All of this you can do, and again rotate upside down, all this is there. That's for your advanced options in copying and moving. And instantiation I've already covered. So yeah, There's one more thing. There's net names. I'll quickly come to that as well. So let's see, you have this, and okay, what net names are is, you just connect all of this. So all of these nets, they're connected to DVD 1.8V. So if I just hover my mouse on the bottom left, check here. Bottom left, you can see the net name. Here as well, you can see the net name, D ground. The internal nodes. So this I've defined, I've called it VN, fine. This I've not defined, so it just gets the name net1, net4, net7, net10. So these are just internal nets, nothing to think much about. But what happens is, let's say you wanted to connect this node to this node. You can very easily do that just by putting a wire like this, and it will get the same net name, net4, net4. What you can't do is name it net4. So now given this name net4, this previous net changed its name to net2. This is still net1, net2, net7, net4. So whatever names are present here, they are not defined explicitly. They are highly volatile. You get what I mean? So if you want to connect to nets by name, you can't use the like cadence assigned names. You have to give them names yourself or like connect them. That's the thing. How do you easily check? Let's suppose I add a net for here as well, giving it an explicit name. How do I check what other nets could be having this name? So do view net highlighting. So if that is on, now this is on. If you hover over anything, it will just highlight all of it this way. So if you have a huge design and you want to see like, is this net going somewhere else as well? So you can use this. There's things like probes as well, but they're more useful in hierarchical designs, and I believe they will be covered later during simulation or something. They can be covered. This is all about nets, net highlighting. One very another simple thing is display dimming. So it's just that whatever net you have saved, only net or like thing you've selected, just that will be highlighted, or like it kept at normal brightness, everything else will be dimmed. So you can do this if like in schematic, some people do this. In layout, almost everyone does this because it can be too much having everything on the same brightness. That's and the small thing, you can just turn this on and off, magnifier, etc. Few like quality of life tools are there. There's also things like zoom in, zoom out. You can zoom in, zoom out with your like scroll wheel. Otherwise, you can do with the square brackets. So you can almost use cadence completely through keyboard as well. Yeah, there's things like check hierarchy, etc. This I will few parts of it I may cover here, and remaining parts simulation. Let's say okay, those are like the important points. Hmm, there's shortcuts. Okay, there's one more thing: instance names. So you have this PMOS. Right now it's just called PM0. So you can change this to be something else. And if you have like some huge design and you are bringing in some block, you're bringing in some op amp or something, it's best to give it some name specific to it, so that in simulation or something it can be very easy to find out where, like, because when you see issues it will tell you that the issue is with PM3 in the hierarchy, and it will tell you the entire hierarchy. So in your test bench, in I2, inside there's the I5, the instance names will usually be like I and then some number, or U and some number. Here M and some number for MOSFETs. So it will just show that. Instead of that, if you keep giving your names, like if there's a op amp, you write that it's a revgen underscore op amp. Inside, if some specific block is there, some buffer is there, so you write I underscore buffer. So you can easily find out that okay, this is the revgen uh, op amp. Inside there's this buffer. Inside there's some PM3. So your work reduces a lot. I would recommend never to, especially for blocks in any hierarchy, never to leave the instance names to just I1, I2. That will create issues for you later and cause headache. Some other smaller things are there. Let's say you want to change the length or width or some properties for all of these together, or just three of these. Let's say the last three you want to change. You can individually change them, or you can press Q for the properties for any of the select things, and apply things to all selected instance of same master. Same master means same PMOS, this PMOS one. Sorry, the PMOS, this cell PMOS. All the instances of these selected ones, and you want to keep this as like 2 micro, let's suppose, and apply. So the selected ones, they got changed to 2 micro. Also you can do is just all instance of same master. So all the PMOSs which exist in it, in one shot you can change them to some other thing. This one. This is also helpful sometimes, and you should know these like mask change shortcuts. There's instance name, model name. In case you're wondering, this is the model name for your PMOS 1. NMOS has the model name NMOS 1. Although they look similar, like the cell name is NMOS and the model name is NMOS 1, these are pretty independent things. NMOS 1, it actually, your simulator looks at NMOS 1 rather than NMOS, and by using the model name it searches for what the NMOS is supposed to be like, what is supposed to be its VDH, what is supposed to be its other parameters, etc. This is what's really important. It will be discussed in more detail during the simulation part. It's just something to be aware of, is the model name. In case you don't have a model name, your simulations may not work. Then okay, all of this is fine. Now I can show how to create a symbol for this guy. So we have an inverter, create cell view from cell view. So this schematic, it's called a cell view in the like, Cadence language. A symbol is also a cell view, an overall inverter base. Inverter base. This is a cell. So create cell view from cell view. We want to create a symbol from a schematic for this library, for this cell name, etc. So okay, pins on the left should be what, pins on the right should be what, top pins, bottom pins. So on the left I want V in, on the right I want V out, on the top I want the DVDD, on the bottom I want D ground. This way. Then okay, it will create this symbol. You can save it. Now how do you create a good symbol? You can, there's like tools like line and all this. You can draw whatever you want and you can add text and all this as well. There's a text option here as well, symbol label, and even you can do like create node shape and all this by pressing N. Same thing as here. So create node, you can add some text here. Otherwise what you can do is go to something like KHDL, take not gate is there, there's a symbol for it, open it, and you can copy this thing. So instead of spending so much time trying to make something like this, you can just copy this guy and adapt your things just for this. So copy, yeah, and move this and all this. Text size also you can change by pressing Q. You can change the size, you can change where it's kept relative to the pin, all this. Other you can just directly move as well. Very simple. Also, this is a reminder to change this apply to whenever you're done with it. Thus it will apply to all things like here it change this as well. So now you've kind of made a symbol and it will work, but this is not ideal. We'll go into detail of why it's not ideal. Because we've ignored a few things here. You can go into a lot more detail about just a symbol because see this. a lot more going on here compared to here. But I personally have never tried CDS parameters and all this CDS term V out all this. But a few like essential things which you should add into your schematic in your symbol is things like part name. So this will just tell you whether like this name it will show inverter base, because you may have an inverter, you may have a buffer, you may have a driver, and all of them could end up having the same symbol. So having a name there can be helpful. Instance name. So like how there's different instance names for these transistors. So PMOS is written, that's the cell name, and PM0 is written is the instance name. So that's the thing, instance name, where it should appear, in what orientation it should appear, what should be the size. All this you can change here by just by doing Q. That's something. One more good thing to do is keep the size of these like texts so that you can look at them from enough of a distance. If they're too small, if you're zoomed out too much, you won't be able to see anything. So even here you can see that there's a DVDD here and there's a D ground here. Previously that was not, and see at this point it breaks. So text should not be so small that it just disappears at a normal viewing level. So even this might not be good, but the names are too big. It's something we will have to, where you'll have to make call. Zero point 0.5 may work. So at this point it starts to break, but here the text size becomes so very, starts to become insignificant. And here you can see that it's ground, that's DVD. That's about the text size. There's things like you can have the library name present in your symbol as well. This I've seen rarely a few people do it, but it's a good practice to do nonetheless. So I have an example here of a symbol. So you can have this. You can write in square brackets at libname. So the library name will also appear there. That's the thing. And one last thing is this is your symbol. There's a red box here. That's your selection box. So I would recommend that whatever initial thing you have, if it's not really relevant, just delete it and create selection box automatic. So now it like fits your symbol correctly. This way. I'll add the lib name as well here. Yeah. Once you have this, let's say you make some mistake and here you've written V out 2. If you try to save it, it will say there are warnings. And when I'm saving this by pressing Shift X, that is the save command and cadence. So it checks whether the symbol and the schematic are matching. If it's not matching, then it will give you these warnings. You can check the warnings by pressing G. So it says like Vout 2 is present in symbol but not in schematic, and Vout is present in schematic but not in symbol. Right now it's just telling you it's a warning, and if you ignore this warning and try to run it, it will just say that we in your simulation it won't work because V out 2 is just some node which doesn't exist in your schematic. So best to not keep any warnings in your, especially symbol. You can avoid having any warnings in your schematic as well, and it will help you debug things faster if there are no warnings with your design. Another thing is one shortcut. You have your symbol, you want to quickly go to your schematic, you can just press equal on your the equal to sign on your keyboard. So it will switch between these two. That's it. Some some minor points are things like, let's see, have a bus. Others will cover buses later. So this now your inverter is done with a symbol as well. Now let's try to make a test bench, and there I'll show some more things about schematics. So now you can instantiate like how you instantiated a NMOS and a PMOS. Just in library test2, you have this inverter. One thing you can't do is have TB inverter come back here again. So even if it had a symbol, you can't put it back. It will say like there's a circular linking, so it won't allow you to do it. Inverter base, that's a symbol available for it, and same things you can do here as well. You can put multiple of them in an array, column, rotate it, mirror it, all this, like the symbol itself, so that it's more convenient for your overall design. So here you can just put it here. One more thing which we have overlooked a bit is, again, very particular nitpick, but see that my mouse is at this point at the center of the screen almost, but the symbol of the inverter is not centered. So that's also something you can change, just a minor thing which you can take care of. So again, so this is this inverter, that's the instance name, part name, your Excel name, and it is coming from test2 library, right? Because if I was taking it from test 1, let's suppose, because there's inverter base there as well. So now you can just very clearly see that which library it's coming from. If you have a large design and there are different libraries for different purposes, then this can be helpful, having the library name appear there as well. You can do things like edit in place. So in case you make all of your symbol and you're not happy with it, that this should be slightly here or something, this should appear here or something. So you don't need to go inside the cell or like search it through the library manager and edit it. Wherever you were seeing it, you can just edit there right away. So as you can see in the top, we're currently editing the symbol of inverter base. But if I go one level up, which is Control E to go one level up, now we're in test bench inverter schematic. Now coming back to things like warnings and no connection. Yeah. So now that I just have this, and this is a test bench, here I can have all of those VDCs for the inputs that I want to give this. I'll say 1.8. And in a test bench, and only in a test bench, I can use the ground, because otherwise it should just be a net. For the sake of the inverter, it is just a net, the ground. But here you can use the ground, ground exclamation mark, VDD. And last thing, there's a V out. So earlier it showed me 4 warnings and 0 errors. Now it is saying there are 2 warnings. What are the 2 warnings? And although you can ignore warnings, it is not recommended. You should know why there are warnings. And at least in your designs, there should be no warnings. In your schematics, you can have warnings, but better to be aware of them. Again, press G to find out the warnings. Seeing the pin V out is floating, and again it is floating. Same issue both. Here it's saying it's floating. How do you solve this? Realistically, V out would be connected to something. Even internally, it has some cap or something. Even outside, when you have some design on a chip, you want to look at its output. You will connect to oscilloscope probe, right? That oscilloscope probe will have huge amounts of resistance. It will have some cap, all this. Right now, this Vout doesn't have anything. And that's why Cadence is saying that, are you sure this is a floating net? There is probably something connected to it. But if you want to tell it to really ignore it, or to make sure that, or just to tell that there is no connection going on there, there's again a like schematic construct which exists in basic library. There's a basic library, and there's no con. So if you connect this here, it just says that on this pin there's no connections, and there are no warnings anymore. You can do check and see. Yeah, it is very tempting to add this to all the nodes so that you never get any warnings, but then it defeats the entire purpose of having these checks in your software. So only use these where it's like essential that you don't add any like additional output load or something. That's the only time when you should use this. And yeah, and at this point you can run the same thing again. Now what hasn't been covered is hierarchy, which I feel can show in a different video. Shortcuts are done. display DRF is one thing. So this about covers your schematics. There's one thing about your display settings. We'll show that through the PDK. Yeah. So there's this file display.drf. What happens is when you have this, you are creating some net, you're creating some wire, you're writing some name. Uh, how does Virtuoso know? How does this software know what color to give this wire? So that all of that is written in this display.drf. Whenever you start your cadence, it will look through like four different places, four or five different places for where to find all these settings. What should be the color of the nets and how do you highlight some warning? All of these like some basic tasks. And whatever file is present in your like your cadence directory where you run your command from, that gets the highest priority. Whatever display DRF file is present there, that gets the highest priority. But whenever you launch cadence and you try to open anything from your GBDK, it does some initialization, which I've showed in the previous video. When it does that initialization, it means that it initializes this display.drf file as well. That's why no matter what display.drf you have in your like home account, in your home of your account, or in your directory, or in your cadence installation, all of that gets overridden by your PDK DRF. PDK's DRF. And I've seen cases where your schematics are basically unviewable. Unviewable because all of these wires will turn out to be just white or black or something, and all these, even these green lines, etc., like they are not visible because the DRF file is not readable by your account. So right now this PDK is stored somewhere in application cadence PDK, and this is handled by your root, by your like admin of your server. It is possible that this file is not readable by your account due to some error, which I've seen happen multiple times actually. Which is why it can happen that you won't see the colors here correctly and all that. A lot of drama can happen. So just to cover that, and even things like if you say there's a blue color, so all the colors are defined here. If you really want, you can change this. And if there are any patterns, if there's a zigzag pattern, what does the zigzag pattern look like? All of that is defined here. If there's a wire, what should be the color of that wire? Line style. So if there's some dash dot, so how long should the dash be, how long should the dot be? Is it goes into extreme detail about all of this, and it is not really that relevant for a schematic, but it is essential for your layout. If you don't have this DRF file, your layouts will basically just be blank. You can consider them to be blank because different metals have different patterns on them in your layout windows so that you can easily identify them. If this DRF file is in there, if it's not readable by your cadence or it's not present at all of them will look the same, and it's hell to figure out what's even happening. So just like putting that out there, in case you're seeing some abnormal things, this could be the reason. And you can just like go to your PDK and try to see this TRF file. Would be kept somewhere near the PDK and see if it's like accessible to you or not. So I believe that about covers it. I'll just show some examples here. So one example I'll quickly show here, not go into too much detail. How do you have a system verilog uh, design? I'm not going into how to simulate it, that will be covered later. But can you have system verilog designs? Can you have just verilog and like run it in the same way as your like schematics? Yes, you can, and you can verify if it's like correct or not by just, so you have this inverter base and it has this schematic, it has a symbol. You can have even more things as I specified earlier. I'll just add a system verilog text. So it comes with this already, that there's these four in-out ports, and I'll just add one more thing, which is this definition here, the what this block will do, that just I've added, and I can now use this in my simulations as well. Okay, yeah. So also really important, it will try to extract it, like it will check if there are any issues if when you try to save it, similar to warnings in your schematic. Here you'll see warnings. Now here it is good that it gave me warning because there is nothing called in, there's a v in and there's a v out. So now it should be fine. And the cadence terminal, you can see extracting and all this shadow of the cell view has been generated, extract completed, all this. If there are any errors, it will show them here in the cadence terminal. Even things like whatever tools it is using to extract this, to figure out whether the verilog is correct or not, if those tools are not accessible, it will be visible. Uh, like those errors will appear here or in your overall like your terminal. So that is something to like look at in case like things are not working as expected. Yeah, and yeah, right now for this guy, for this test to inverter base, there is already a symbol here. Let's suppose there was no symbol for it. Then after the extraction is done, it will say, do you want to create a symbol? Maybe I'll just show that. Delete the symbol. So now I just have this verilog here, and I'll extract it. Yeah, so cell view, this symbol does not exist. Do you want to create it? Yes. Now it just created a symbol using like some default options. Again, you can edit this. You can do the create cell view from cell view. All of that is still there. Here as well, you can do create cell view from cell view to symbol, and the like same dialog box and etc. You'll see. You can do replace, and then yeah, left right pins, all that. Okay, so I think that covers how to make schematics and like the best practices associated with making schematics.